I will talk about Joule heating in bad metals. Okay. So just to spend a few minutes with an introduction, a little bit to explain why I am talking about what I'm talking about. And so my personal motivation came from this work. This work we did a year ago, or a couple of years ago actually, with my student Connie. So take LSCO, okay, and go way overdoped past the superconducting dome, okay. And this is actually some old data from Hussey that he kindly sent us. And so let's plot the derivative of the resistivity against temperature, okay. And this is temperature, okay. And so this is overdoped, there's no superconductivity, and is in the low temperature regime, the fact that this is a line with zero intercept, essentially, that's the derivative, so that means the resistivity is going like t squared. And that makes sense, right? You're far overdoped, there's a t squared resistivity at low, a pure t squared resistivity, no t linear term at low temperatures. However, at about 150 Kelvin or so, there's sort of some kind of feature. And if you look here, it has a line. This is noisy, right? Because it's the derivative of the resistivity, right? You just take the data points, you take the differences, and you plot them. And so the fact that there's now a line with an intercept means that in addition to a t squared term in the resistivity, there's also a t linear term, okay? Now, t linear resistivity is sometimes interesting, but the one case where t linear resistivity is very well understood is in, copper or something, where t linear scattering appears at about 1/3 of the Debye temperature. And in LSCO, about 150 Kelvin is a pretty reasonable estimate for about 1/3 of the Debye scale. And so it's very tempting to understand this feature, which is the onset of a T linear resistivity, as being the appearance of a phonon mode that is scattering at this temperature. Then you can start lowering the doping and going towards critical doping. And then what's a bit interesting is the feature remains at about the same, at around the same temperature, but at low temperatures, this intercept starts going up, okay? And so that means there's a T-linear term also at low temperatures, which maybe many of you are familiar with, that in LSCO, there's this anomalous criticality where there's a regime of T-linear scattering at low temperatures. And as you go towards critical doping, these two lines meet and they become straight at about 0.2, all right? And that's a bit interesting because this T-linear scattering, which the simplest, the most vanilla explanation is it has to do with phonons, and this T-linear scattering, which is surely not phonons, somehow meets at this critical doping. And okay, so just to maybe contextualize this, let me show you again. This is this plot of LSCO, and they're plotting these colors are the logarithmic derivative of the spectral temperature, so that it's supposed to be some exponent. So this is supposed to be t squared, this is supposed to be T linear. What I'm telling you is that if you don't do a logarithmic plot, but just do rho dt, you'll see a feature, this kink I showed you is roughly along this line, okay? And above, so if you stay here, it's t squared, but above here, there's a T linear component, that turns on, okay? And if you can follow this T linear component down, this is the low temperature T linear component, and they kind of merge at sort of this critical doping. Okay, if this seems like the simplest explanation of things, but if it's true, it means that at least up here, there is some phonon scattering that you can see quite clearly in the resistivity, which is not something that's normally discussed in the context of cuprates. And so this is all motivation, okay? So what this led me, I think it's really important to disentangle the role of electrons and phonons in strange metals. And to do that, it would be nice to think about an observable. So, resistivity is complicated. There could be electron-electron scattering, there could be electron-phonon scattering. I'd like to think of a different observable where phonons are absolutely essential, okay? And so we're gonna look at a different observable where phonons are essential, and then we can directly see whether electron-phonon scattering is important or not. Okay, that was the motivation. So one process where electron-phonon interaction is essential is for Joule heating. And so the picture, I'm imagining something like this. This is your electronic system. It's coupled to a lattice, and then there's the bigger environment. So the electrons, of course, interact among themselves. they also scatter off the lattice. The lattice also scatters off itself and equilibrates with the environment. If you apply an electric field to the system, what you're going to do is you can, or in any other way you want, you can pump energy directly into the electrons, and then you can ask what happens. So one thing that can happen, of course, is the electrons interact among themselves and thermalize electronically, but they can also dump and eventually they're going to have to dump the energy somewhere else. And the lattice is the first place that is going to dump the energy. And so this process of dumping energy to the lattice is crucial, can only happen because of electron-phonon coupling. And so it's a process in which you can evaluate the strength of the electron-phonon coupling in a strange metal. Very good. And we're going to consider situations where the electronic interactions are strong. So this thermalization happens quickly. The lattice in the environment also thermalize quickly. And then the bottleneck is this process where the electrons have to dump the energy to the lattice. So let me quickly show you two experimental consequences. So there's a time scale tau over which the electrons are able to dump the energy to the lattice. Okay. So let me give you two experimental processes that measure that crucially depend on this time scale. So the first one is Joule heating. So you pump an electric field, pumps energy into the electronic subsystem. And so that's this equation, right? So you have, this is the Joule heating, right? E dot J, and so that's changing the energy delta E of the electrons. And so if you have a closed system and you apply an electric field, it just heats up to infinite temperature and there's no steady state. So if you want that to be a steady state, meaning that ddt is 0, then there also has to be some process where the electrons get rid of their energy, right? Because if pumping energy in, it's got to go out. And so this term describes that, and tau is this time scale over which that happens. And so in a steady state, you have to balance these two terms. Okay. So you apply an electric field, you balance these two terms, but the electrons will get a little bit hotter because you've pumped in some energy. So the change in the temperature of the electrons is the change in their energy over the specific heat. And now by balancing these two terms, the change of the energy is E dot J, the rate at which you're pumping in energy, times this time scale at which you're dumping energy. And then using Ohm's law, J is sigma E. And so the shift of the temperature, so the electrons are a little bit hotter, and the shift in the temperature goes like E squared times this time scale. Now, this leads to a non-ohmic current because the conductivity, the current is sigma times E, but this tau, this temperature is shifted by delta T because the electrons got a bit hotter, and this produces this E cubed term, just this E squared times E times tau. Okay, so all this to say, there's a universal non-ohmic response that is that's proportional to this time scale at which you can dump things into the lattice. So for example, if you take a closed system, tau goes to infinity, and there's no regime of ohmic coupling, because if the time scale is infinity, the electrons just heat up, right, to infinity. There's no steady state. So to have Ohm's law, it's essential that this time scale is not 0. Once it's not 0, though, then you can take the low field length and you can just concentrate on this term. Okay. So for Ohm's law, Joule heating is essential, but it's higher order in E, but it goes like tau. Okay. Anyway, so this is one observable where this tau appears. Another one is if you probe spectroscopy. So here you hit the electron, you send in a pulse of energy. Because the electrons have a lower specific heat, most of the energy goes into the electrons. The electrons heat up much hotter than the lattice, and then they start cooling down. And then what you do is you do another spectroscopic measurement as the lattice is cooling, as the electrons are cooling down, and you can follow the decay of the electron temperature over time tau. So for example, this time resolved up goes like this, and so here's an example of a plot on a cuprate. And so these different lines are time. So you whack the electrons, they get very hot. So early time is this thick curve that has a bigger temperature, right? That's the width of this line is the temperature. And as time passes, it gets narrower because the temperature is going down. Okay, so essentially by measuring the evolution of the Fermi-Dirac distribution, you measure the temperature as a function of time. Okay, and so then you can plot the electronic temperature, right, which is as a function of time. And so you plot it, this is electronic temperature, against time. You whack it, it goes up, it falls down. And so from this initial decay, you extract this time scale tau that I'm talking about. Later, more complicated things happen because there's also lattice. Lattice and harmonicity is also important. But this initial decay here is due to this time scale. Okay, so there's a time. So that's great because it means there's a physical process that gives you direct access to the electron-phonon, the effective electron-phonon interactions. Okay, very good. So of course, all this was known a long time ago, at least in the Soviet Union, and so Kaganov, Lifshitz, and Tanatorov calculated this time scale tau for weakly interacting electrons coupled to a lattice. And so it's very simple. You do a simple scattering process. And so this is what you get. So this is the rate at which electrons can free electrons dump their energy to a lattice as a function of the temperature over this Bloch-Gruneisen scale, which is the natural for an acoustic phonon. This is for scattering into an acoustic phonon. Okay, and of course, this whole thing is proportional to the electron-phonon coupling. Right. So yeah, this is. Sorry, I probably set the electron-phonon coupling to 1 in this plot. And so it goes. So let's just understand the two limits. At low temperatures, the time scale is small because there are not many phonons at low temperatures to dump energy into. And at high temperatures, the rate also goes down because high temperature scattering of phonons is elastic. When you're above this Bloch-Gruneisen scale, the scattering with phonons is elastic, and so you also cannot dump energy efficiently into a lattice at high temperatures. Okay, so so it looks like this. Oops. You get a peak, and this is this peak at roughly the Bloch-Gruneisen temperature, some fraction of the Bloch-Gruneisen temperature. If the electron-phonon coupling is a typical value for a non-superconducting metal, this rate is Planckian. It's kT over 8 bar. All right, so that was all known. And so now let me tell you, however, I would like to understand this process in something like cuprates. And in cuprates, the electrons are not free, okay? And so it's not obvious that this formula applies to cuprates, right? Because this uses free electrons, the electrons are not free. So let's see. So both Monte-Carlo numerics, which I'll mention again later, and also just experiment suggest that in strange metals, the density spectral function, which is the thing that is going to control how well the electrons couple to the lattice, it does not have the Lindhard form, which is this free electron form. Given that the density spectral function is not the Lindhard form, that's obviously going to impact the electron-phonon interaction because the phonons. I'm mostly thinking about it. I don't have to think about acoustic phonons, but for specificity, I'm going to talk about acoustic phonons mostly. So what's the formula that you should use if the electrons are not free? Okay, what's the rate at which strongly interacting electrons? So we assume that the electron interactions are much stronger than the electron-phonon interactions. So the electrons equilibrate first. How quickly do those electrons dump their energy into the lattice? Okay. So I'm going to show you in a minute a formula. This is work with Paolo Glorioso, who's a postdoc at Stanford. A formula and what it's going to depend on is the density spectral function of the electrons. Right? This is an object that is determined by electronic interactions when they're strong. So if you know this, we're going to plug that in and you'll get the rate at which you dump energy. Now, the assumption, of course, to do a calculation, there needs to be some input, okay? And so the input is going to be that this time scale tau at which you dump energy to the lattice is much longer than the time scale over which the electrons equilibrates, right? So the electron which is in some strongly correlated regime, that's exactly where you want to be, right? The electron interactions are very strong. All that happens first, and then on a longer time scale, you dump energy into the lattice. When you're in that kind of regime, that's when these sort of universal quantities like the density spectral function will control everything. So let's do it in 2 steps. And so here there are 2 technical slides, and then that'll be all. So this is the formula. Okay, this is the Kubo formula for this relaxation time in terms of E dot, where E is the electronic energy, which is not conserved because of coupling to the lattice. Okay, this comes from this form. So if you're in this limit where the electrons equilibrate very quickly, the only time scale left is this. It's like almost like a Joule-like form, except this tau is not momentum relaxation, but energy relaxation. Okay, it's the same in Joule. It's the same idea. Everything equilibrates, then momentum takes longer to equilibrate, so you have a momentum relaxation time. This is not the momentum relaxation time; it's the energy relaxation time from coupling to the lattice. And so from this you can quickly get this. Now, it's useful to have E dot here. So this uses this sort of memory function type method. So E dot, right, is the rate of change of the electronic energy due to the total Hamiltonian. The part of the total Hamiltonian that doesn't commute with the electronic Hamiltonian is the electron-photon interaction, right? So E dot is the electron-photon interaction with the electronic interaction. I should have written this down. So, okay, so the electron-photon interaction is some potential V that couples to the density. Okay, and so now you have the coupling of the electronic. Now V, this bit only depends on phonons. This bit depends on the electrons, and so it's the commutator of the electronic Hamiltonian with the electronic density, and that's just N dot. Okay, so what you have to do is calculate the 2-point function of this quantity, where this. Okay. So Vk is going to be this you can put in any electron photon coupling you want. Okay, if you want to couple it to spin, like in this earlier talk, you can do that. As an example, I'm going to take a deformation potential. So this is now some phonon raising operators. This is the usual stuff. Okay, so now we take this and you plug it into this formula. All right. Hopefully this is very intuitive, okay? Just saying the rate at which you dump energy into the lattice is a 2-point function of E dot, okay? Where E dot's the rate of change, the energy. So you do that, and you assume that the lattice is in equilibrium, and so you get this formula, which I'll talk you through because it's very intuitive. So this is the time scale a specific heat wants to appear, because this is the energy. It's really temperature that wants to appear, so that's why there's a specific heat. This is the electron-photon coupling, essentially. You integrate over all momenta. At low k, it's suppressed because it's an acoustic phonon, and so it couples derivatively. It's a k squared. This tells you how many phonons there are. Omega k is the phonon dispersion. This just tells you how many phonons there are with omega k, and it gets exponentially small if omega is above the temperature, right? It's just so you populate. You can populate phonons whose energy is less than the temperature. And then there's this quantity, which is the density spectral function, which says how many electronic excitations are there that can emit a phonon with energy omega k. All right, so you integrate over the rate at which you dump energy to the phonons. You integrate over all momenta of the phonon that you emit, right? There's a Boltzmann suppression factor. There's a derivative coupling suppression, and there's electrons. So all of the electronic information just has to come from this factor. Okay, so you then have to take your favorite strongly coupled system, the Hubbard model, twisted bilayer graphene, whatever you think it is, and you calculate this quantity, and then you can just plug it into this formula. Okay, so as a sanity check, let's do the free fermion case first. So for free fermions, this density 2-point function is the Linhard spectrum, and it looks like this. Here's omega, here's k. There's a continuum of particle-hole pairs. Okay, so what does that formula tell us to do? It tells us to take the phonon dispersion, right? Phonons are much slower than electrons, and you integrate this line against the blue line, against the blue region, right? So all this blue region is where the electrons can emit a phonon, and the orange line is where the phonons are, and so you basically integrate along this line. You do that, and you'll get the Soviet formula exactly, right, with factors of 2 and everything. Okay, so this formula is correct. Right? However, the reason we developed this formula was to use other things that are not the Linhard continuum. So, so I'm now going to show you 2 examples of that. But this is the main point I'd like to make. If you think you know what this density spectral function is, and you think you know what the electron-phonon coupling is, okay, then you can use this formula, right? I'm now going to show you two examples of how to do that. So, for example, there have recently been measurements in Nabisco of this quantity, okay, using this EELS, and you know, they're not ideal. They're still at somewhat high frequencies, okay. So I'm just illustratively going to show how you should use this formula. So this basically the important point here was that it really has a very weak dependence on K. So there's a K squared at the front, but this omega C, this thing is basically constant. Okay, and so this is an experimental result. All these numbers, big A, little a, omega C, they're all known from the data. So we can just take that and plug it into this formula and assume something, for example, seeing as this is only valid above 0.1 eV, which is a bit high. Let's just say there was an optical phonon at that energy scale. You could plug that in, assume the electron-phonon coupling is order 1, and you'll get a time scale that comes out as about 0.1 picoseconds. Okay. So let me just go back a minute. You know, 0.1 picoseconds is a very reasonable time scale for these kind of processes. Okay. So actually, if anything, what that tells you is that even though the spectrum is completely coherent, right? There's no 2KF singularities or anything. You actually get a ballpark, very similar time scale for dumping energy into the phonons. Okay, so incoherence. So first lesson is that incoherent spectra can dissipate into phonons at comparable timescales to conventional metals. That means if you really want to use this formula precisely, you need to know quite precisely what the electron-phonon coupling is, because it's not about orders of magnitude; it's about factors of 2 and so on. Okay, which brings me to a point. So this formula, it turns out, is particularly useful for bad metals. So let me remind you what a bad metal is. So here's a conventional metal. Okay, this was remember last time I had a non-interacting metal. You had this Lindhard continuum. And you can say, suppose I take the Lindhard continuum and I add weak interactions. How does the density 2-point function change? Well, what interactions do is introduce a mean free path, okay? And interactions are important on length scales bigger than the mean free path, right? Because the electron has to collide a few times before it knows that it's interacting. So large length scales are small wave vectors, okay? And so what interactions in a weakly interacting metal do is they will only change this density 2-point function at K that is smaller than roughly the mean free path. Okay, and so the fact that in a weakly interacting metal, the interactions only do stuff here, but this integral, you also emit phonons at quite large K, and those large K, the electrons sitting at large K don't know about the interactions, right? Because they're very short wavelength, and so the conventional formula doesn't get changed by weak interactions because most of the emission of phonons comes from large K that are not so sensitive to the interactions. However, a bad metal is defined to be a metal where the mean free path becomes of order KF, okay, of order lattice spacing. In that case, the interactions go all the way up to a large scale, and so I think the definition of a bad metal should be that the Lindhard continuum all gets eaten up by interactions. Okay, I think so. That's right. Okay, so in a bad metal with a short mean free path, interactions occupy a much wider range of K space, and that means that the integral along the phonon dispersion is all within the interacting regime. Okay, and so indeed the Kaganer-Redal formula should be quite changed. Okay. So as another example, they're not of a measurement in a bad metal regime is from a Hubbard model. And okay, sorry, I should have said something. So a nice thing so this is an interacting regime, and in principle, a lot of things can happen in an interacting regime. However, if you're deep enough in the interacting regime at the lowest energies and the longest wavelengths, then this density 2-point function is expected to have a universal form, which is diffusion, right? On the longest time and length scales, charge has to diffuse. And so if this regime gets big enough so that most of this region is deeply in an interacting regime, and then this function, this guy, is expected to take quite a universal form, right? So, and this was seen in this cold atom experiment that I'm about to tell you or remind you about. So this is a cold atom realization of the Hubbard model. And so they have, and so what the experiment is they set up some profile of charge at time. So these are the atoms in the trap, and there's a wave, right? There's an oscillatory density. The density is modulated with some wave vector, and then they let go of the modulation and they watch the profile relax, right? And so this is the amplitude, right? So this is the profile relaxing as a function of time, right? They're taking photos, and this is, right, this is the relaxation as a function of time, and these lines are different wave vectors, okay? And so it turns out that this whole plot notes that it overdamped for some wave vectors, but for the shortest wave vectors, it actually oscillates, okay? This is a characteristic sort of diffusive to sound crossover, and this is all captured by this formula. So the data, this data is fit, and so in this paper they fit it, and they extract the diffusivity, the momentum relaxation, this time scale, and this susceptibility. And so look, this is a very reasonable formula. If you set this term to 0, it's a diffusive form, okay? But if you set this term to 0, it's a Drude form, right? So this is a minimal formula that interpolates between a Drude response at k = 0 and a diffusive response when omega is small. Yeah, I think first written down by Kadanoff and Martin a long time ago. Okay, so they measured this form, okay? And so they are, now, this is the Hubbard model at quite high temp. It's a cold atoms, which means they're at quite high temperatures, okay? But that's great. That's the maximally incoherent regime that we'd like to probe. Okay, so they measured this, and they have the d, the chi, and the tau are all known experimentally, and so we can again plug it into the formula. And let me just show you. I'm just trying to illustrate the differences. So this is temperature, and this is this time scale tau. Okay, this is the time scale. I've divided out the electron-phonon coupling, and there's some Debye temperature here, but that doesn't matter too much. This is the time scale. And so this is what you get from the experimental results. This is what you would get if you took the Lindhard formula and put in the parameters. I mean, they know the density, they know all the mass, all these things are known, and you get this. I've ended it here because EF. This is EF. Okay, these are really high temperatures. These are non-degenerate temperatures. Okay, so down here is the degenerate regime. So again, it's not orders of magnitude, but it is different, right? So in principle, if you really know what the electron-phonon coupling is, and you think you know what the density two-point function is, you should be able to measure these things. I should say this result, this form, is also consistent with Monte-Carlo simulations of the Hubbard model. Good. So it's a simple story today. So I have a Kubo formula for the rate at which electrons dump energy into the lattice. And the important thing is that we do not assume weak interactions. It's a different simplification. It's not weak interactions. In fact, it's strong interactions. Okay, this formula is true when the rate at which you dump energy is the slowest process. And this is a measurable quantity. I illustrated the use of this formula on 2 measured incoherent, meaning non-Lindhard density spectra. And so one possible thing this could be useful for. So suppose you believe, as I think most people do, that the essence of strange metals is electronic. It doesn't have to do with phonons, okay? Then you should be able to measure or calculate purely electronically this time scale. Then ideally, you would measure tau. And from knowing, if you know this quantity and you measure tau, then what you determine is the strength of the electron-phonon coupling via our formula, right? So here, what I'm saying is that if you know this, and you measure that, then you get this, right? You'll get this, the strength of the electron phonon. If that number that you get is too big, okay, then that falsifies the idea that the phonons are not your starting point, right? Which is the electronic interactions were stronger, okay? So what I think really, is that it? Yeah. So to go back to where I was at the beginning, I think I would really, if this kink has to do with phonons or not, one way to try, I'm saying one way to try to determine that is to independently measure the strength of the electron-phonon interactions and see if it indeed predicts a resistivity scattering with the right magnitudes here. Okay. All right. Thanks a lot.